So as I was saying in the previous video, 1/3 of those waves will be able to get through and will be unobstructed. So essentially we end up with constructive interference. All right. So constructive interference. And the pattern continues. So I'm not going to do the next one because it's just developing the pattern for you, and I'll tell you the pattern does continue. So that's why the intensity decreases when you move outside, because only 1/3 of the light waves are not being taken out of the equation here. 2/3 of them are experiencing destructive interference. So it's still a situation of constructive interference. It's just less light waves are available to do this. So some equations here. So just developing, we know delta L is equal to, well, looking at the pattern here, the first one we're doing is constructive interference. So it happens at 3 lambda over 2. The first one is actually lambda over 2. It's just tough for me to show that geometrically. It's easier to divide the triangle into 3 than the 6, because then it's a little bit trickier for you. So we get lambda by 2, 3 lambda by 2, etc., etc. So we end up with a arithmetic sequence or pattern here. It means that we're adding a full lambda each time. So therefore, delta L then can be calculated by simply taking lambda, and it's always going to be some value minus 1/2, where that n value has to be an integer value. All right, actually it's got to be, I'm just going to say it's a natural number, one of our counting numbers. Okay, so there is your delta L. That tells you how much of a separation has occurred. Now, if I go back and use the one that we didn't use, just to show you the math or the geometry here. So we have our central line, and then I had that line on the angle, and then we have that line coming down, our incident ray. I told you that this was theta, and subsequently then, the right angle triangle that's formed has this angle of theta. So that being said, we said that this is delta L, and we said this is our W. So we can use SOHCAHTOA to find a relationship between our theta, our delta L, and our W. All right, and from that, we get the relationship that sine theta equals delta L over W. And that's true for both equations, but specific to this one, sine theta equals the lambda n minus 1/2 over W. So there's one of our equations, and you got to make sure it's clearly marked that this is an area of constructive interference. Similarly, for destructive interference, first one occurred at lambda, then 2 lambda, 3 lambda, and so on and so forth. Again, the pattern is adding lambda. So that reduces it down to delta L is equal to n lambda, where n, element of counting numbers, are natural numbers. So when we take that original equation, the trig relationship here, to get destructive interference, the angle would be just simply n lambda over W. And there's our second relationship or equation that we're going to carry forward into some of the examples. Now, before I do get to an example, we're going to do some theoretical math for you here. Some people are going to just accept, and some people are going to want to know a little bit more. But let's take a look at a right angle triangle and talk about what happens when a particular value gets really small. So L is our distance to our screen. H is the hypotenuse of this triangle, and x1 is the distance from the center line to the maximum or minimum. All right, so this is our screen. Here's the slit. So we're looking at that angle theta. So if x1 is really small, so if x1 becomes really small, we can say, therefore, the hypotenuse is pretty much the same as the L, the length from the screen. All right. So what that means is that sine theta will equal, according to the triangle I have in front of me, opposite over hypotenuse, so x1 over h. But that would also mean then that h can also be replaced with an L. All right, because of that assumption we made up here. All right. So if hypotenuse and length, the adjacent side, are approximately the same length, then our trig ratio can be written like that. So what does that help us with? Well, we use this approximation and look at our previous equation. So I'm going to take the destructive interference example. So we have sine theta is equal to n lambda over the width. Well, sine theta now is equal to x1 over L. All right, x1 over L n lambda w. So I've just replaced sine theta. All right, so sine theta got replaced with the equivalent ratio. So I'm just playing around here. And what we do is we isolate x1 to get L n lambda over w. So that's one of the relationships I'm interested in. Then we can look at the next maxima. So x2 over L is equal to, or I guess the next dark band, I guess, would be not just n, it's going to be the next one. So we're looking at the dark band beside the one we just looked at. So x1 is the first dark band, x2 is the next dark band. So x2 then will equal L n plus 1 lambda over w. So there's that second relationship. And what I want to do then is I want to come up with an expression to talk about the distance between dark bands or bright bands. So I can just then say, well, delta x is going to be x2 minus x1, the difference in those two distances. So x2, L n plus 1 over lambda over w minus L n lambda over w. So I can common factor out the L, the lambda, w, and that leaves me with n plus 1 minus n. And what we find is that the distance between dark or bright bands is simply going to be L lambda over w. So there's one of your final formulas to add to your cheat sheet. So remember, make sure this is clear, this is the bandwidth between consecutive dark slash or bright fringes, excluding the central maxima. All right, so that allows us to move into some examples. Okay, so for the example here, we have a slit with that width. So I know the width, 2 times 10 to the negative 5. Red light, which just basically tells me my wavelength. So A part, at what angle? So we're looking for an angle, so it has to have theta in it. And so you're looking through. And third order minima. So third order tells us our n value. N is going to be 3. And we're looking for a minimum, so you need to make sure you pick sine theta equals n lambda over w. So that's the destructive interference. So we get sine theta equals 3 times 6.2 times 10 negative 7 over the width, which is 2 times 10 to the negative 5. Going through and using your calculator, you should get 4.4 degrees. All right. B part, third order maxima. So we're just demonstrating how the formula works. N still remains 3 for B part because it is a third order. Sine theta, the key here is because it's asking for maxima, you need to pick the correct formula. So that's your lambda n minus 1/2 over W. So it's just picking the right formula. Once you have that, it's just an exercise in calculator work. 6.2 times 10 to the negative 7. 3 take away 1/2 over the 2 times 10 to the negative 5. Make sure your calculator's in degrees when you're calculating this. And we get 5.3 degrees. All right, straightforward, using that formula to calculate your angle. So that is a measurement of from the center line. So if this is my slit, here's my center line, third order. So there's the angle theta. So we have our central max, the bright. Then we have a dark, which is backwards, bright, dark, bright, dark, bright. So we have our first, second, third bright. Well, we're looking for a third maxima or third minima. Okay, which makes sense that the bright one happens next. Okay, last example. Light from a laser, wavelength 6.7 times 10 to the negative 7 meters, passes through a slit. Width 12 micrometers. It's probably the number they're going to give you in the textbook. Go from micrometers to meters. It's just take the number given times 10 to the negative 6 meters. Always works that way. And it projects on a screen 30 centimeters away. So we know capital L. L is the distance from the slit to the screen. All right. So A part, how wide is the central maxima in degrees and then in meters? So central maxima, what we're going to have to do is we are going to have to find the angle for destructive interference. All right, because we'll have our central maxima, and then we have our dark regions on either side. So if we can find that angle there, double it, will give us the width of that bright region. So that's why I'm actually using destructive interference formula here, where n equals 1. So sine theta equals 1 multiplied by the 6.7 times 10 to the negative 7 over 12 times 10 to the negative 6. So we find that theta is 3.2 degrees. Therefore, width is 6.4 degrees. The second part then, so that was AI, the second part in meters. So how do you do it in meters? Well, that sine theta equals n lambda W formula. We can still use it, except we can replace it, the sine theta, with x1 over L. So that's one of the formulas we had from the previous screen that should be identified. Having that, sine theta equals, we're looking for x1, L was the 0.3. Oops, and we know, we know the angle, sine 3.2. So we got to use the answer from above to solve for x1, and we get 0.017 meters. Now you got to double that, right? Same reason. So we found that distance there. So therefore, central max is 0.034 meters wide. Finally, B part, do it in here. What is the separation of adjacent minimas? So they're basically saying how far apart are your minimas? L lambda over W. So 0.3, 6.7 times 10 to the negative 7 over your 12 times 10 to the negative 6 calculates to 0.017 meters. So therefore, distance between is 0.017 meters. So over here tells you the distance from this dark one to the next dark one is the 0.17 meters. And there we are. There's the homework questions in the bottom. If you have any questions, make sure you ask, and we'll see you tomorrow. Good luck.